Let's start our discussion of proof theory with a naive question. What is a proof? All right, I'm going to give you an intuitive definition of a proof. This is not intended as a formal definition. It's intended to get us started down the road to understanding how to construct a proof. So suppose we look at a fairly straightforward argument from the textbook. If you give me one of your enchiladas, then I'll give you a taco. You are giving me one of your enchiladas, therefore I'll give you a taco. So plausibly, we could formalize this as E standing for you give me one of your enchiladas. Here's our material implication operator, and T, which is the proposition, I'll give you a taco. E is repeated. You are giving me one of your tacos, therefore, one of your enchiladas, therefore I'm giving you a taco. So now if we take this argument, which is an argument composed of actual statements, and we derive a schema for that, for the series of statements, then we will have the logical form P implies Q, with P repeated here, and the conclusion Q. So how did I get that? So basically it's starting with the atomic propositions. I assign P to the capital E, and so it has to be assigned everywhere. And I assign Q to the capital T, and it has to be assigned everywhere. So that gives us this schema. The schema is always written in terms of variables, right? Okay, so now let's do some thinking about this schema. If we construct a truth table for this schema, what do we find? We find that the argument P implies Q, P, therefore Q, is not invalid. How do we know that? Let's do a short truth table. So the short truth table method starts by the assumption that the argument is invalid, which means the premises are true and the conclusion is false. And then it assigns truth values to the individual variables to try to make that assumption work out. So if the conclusion is false, Q obviously has to be false. If it's false here, it has to be false everywhere. For the second premise to be true, P has to be true. If it's true here, it has to be true everywhere. But now look what's happened. If P is true and Q is false, which is what we need to make this premise true and this conclusion false, if P is true and Q is false, then the first premise is false. The only way to fix it is by causing a problem elsewhere. So for instance, we could change P to false here, but if we do, it'll be false here. And if it's false here, then it falsifies the assumption we made that the argument is invalid. So how should we diagnose this? Well, we should say that it's not invalid. Okay, and if this argument is not invalid, then informally we can say it's valid. So now let's think about this. This is a small, valid argument form. And so one way to think about the original argument about enchiladas and tacos is that it's an instance of this argument. So how am I getting that? Well, think about the places that propositions fill. So for instance, we have a front end and a back end of a material implication. The front end is repeated exactly as it appears in the first premise, and the back end of the material implication is repeated exactly as it is in the first premise. So it's like this. The form, the logical form, is repeated. So let's have a look at that. The logical form is just this, implies this. We repeat the front end, and we conclude the back end. Anytime we have an argument in this form, in which propositions go in the geometric figures, then this overall logical form is valid, as we've just proved with the short truth table. In fact, this is such a common argument form that can be recognized all over the place in ordinary language and arguments that people make, that it actually got a name. In the medieval period. It was named modus ponens. So modus ponens is basically the method of positing or putting something in place, and that's because this part of the modus ponens is a conditional, an if-then statement, and this is the thing that's being posited or put out as a claim. So in other words, if we have an if-then statement and we have as a claim the front side of the if-then statement, then we can conclude whatever is the consequent in that if-then statement. And that's exactly what happens here. The claim about enchiladas, remember, it's you give me one of your enchiladas. And the claim about tacos, remember that, I'll give you a taco. Those are joined together by the material implication. That's how we get if you give me one of your tacos, then your enchiladas, then I'll give you a taco. So that's the conditional part of this, the if-then part. And then this is the part that's posited. You are giving me one of your enchiladas. That's posited. And so the conclusion that we're entitled to draw is this backside, or the consequent of the material implication. So one way we could justify the validity of this argument is by saying that it's an instance of modus ponens. Since it's an instance of modus ponens, and it follows the form of modus ponens exactly, then it must be valid if modus ponens is valid. So the basic idea behind a proof is that we're giving a justification for the validity of one argument by appealing to sort of like mini arguments, mini as in M-I-N-I, arguments that we've already established as valid, and we're adopting those mini arguments as more or less like rules. And then we're appealing to those rules to justify a particular argument's validity. So a more formal way to talk about this process is like this. We are adopting modus ponens as an axiom. In other words, we're going to just accept it. We're going to just embrace it as one of our rules for proving validity. And we're going to use a series of axioms to construct proofs that demonstrate the validity of arguments whose validity isn't known. Okay, so the basic idea then is we're going to use these axioms to prove validity by applying them to the arguments, just like we did here.